All right, this is the second section in this chapter. We're going to talk about what is called the fundamental theorem of calculus. This is one of the two fundamental theorems of calculus, and it's the only one we need to cover. There is a second one, but we don't need to cover that in this course. So let's talk about what that theorem actually says. All right, if I have f of x and it is a continuous positive function over the interval from a to b, then the area under the curve between x equals a and x equals b is given by this notation right here. So this little funky s that's in front of my function is actually telling me to take the antiderivative. This is the notation for taking the antiderivative of f of x. And the dx simply tells me, well, it tells me two things. It tells me that that's where the function stops, and it also tells me that x is the variable, the independent variable of that function. So what this notation says is I will take the antiderivative of f of x, and what the a and the b stand for, that is, first of all, that's where the interval starts and stops. But those are also the two x's that I'm going to plug into the antiderivative and then subtract the results. All right, so that is the fundamental theorem of calculus. It's basically saying find the antiderivative of that function, plug in b, plug in a, and subtract the results. And what you will get is the area under the curve, or basically between that curve and the x-axis, and between x equals a and x equals b. There's some properties that we need to know about using this funky s notation. And so, but before we do that, we're talking about, this is basically what I just said. If capital F of x is the antiderivative of little f of x, then this is what I was saying before. We're going to take the antiderivative of f of x, we're going to plug in b, we're going to plug in a, and we're going to subtract the results. And that's how you calculate this antiderivative, or this funky s symbol right here. Okay? So, there are some properties that we need to address. The first one is that if I am taking the area under the curve f of x from a to a, well, I'm not really going anywhere. I'm starting and stopping at the same x value, so the area there will be 0. Also, another property you need to know is that if you go from a to b, or if you go from b to a instead of going from a to b, then the area under the curve, even though it's not really, it's hard to think about areas as being negative, but if I go from b to a instead of from a to b, then the area is going to be the negative of what I would have gotten if I had gone from a to b. Also, if my function is being multiplied by a constant, then the area is being multiplied by that same constant. So this saves you a little bit of time. If your entire function is being multiplied by a constant, you can pull that constant out and multiply by it after you've taken the antiderivative. Also, if you have just this function c, if you have a constant function, then the area of that constant function is going to be the constant times b minus a. Then this property says if I take the area going from x equals a to x equals b, and then I add on the area from x equals b to x equals c, that's the same thing as taking the entire area from a to c. All right, and then the last property says that if I've got two functions, both going from a to b, and they're being either added or subtracted, I can separate those into two areas, take the area of f of x and take the area of g of x, and either add or subtract them depending on what was happening in the original question. So you can, you can separate these integrals into separate areas and add or subtract them according to what the question was asking. So all that's well and good, but let's do some examples just to clarify anything. So if I am using the fundamental theorem of calculus to find the area between the x-axis and y equals x to the third from x equals 0 to x equals 2. So x to the third is going to be my f of x, my a is going to be 0, and my b is going to be 2. So let's see what that looks like. if I plug everything in. So my 0 and my 2 go on top and bottom of that funky s symbol, and x to the third goes inside between the funky s symbol and the dx. Alright, so if I calculate what the antiderivative of my function is, I have to do that first. The antiderivative of x to the third is 1/4 x to the fourth. Okay, so that's what I have to plug my a and my b into. So the antiderivative of x to the third is 1/4 x to the fourth. So once I've calculated the antiderivative, I don't need the funky s anymore. I don't need the dx anymore. I've just got this function, and I put it in square brackets, and on the outside I write what my a and b are going to be that I'm going to plug into that. So remember, I plug in the b first, so that's my 2. I'm going to plug 2 into 1/4 x to the fourth, and then I'm going to plug in 0 into 1/4 x to the fourth, and I'm going to subtract those. So this ends up being 4, this ends up being 0, so 4 minus 0 is 4. So that's the area between the x-axis and x cubed from 0 to 2. Alright, and let's see what we are talking about next. Another example, we're using the fundamental theorem to find the area between the x-axis and y equals cosine x from 0 to pi over 2. So remember, the first thing I need to do, this is actually what it would look like in proper notation. So I'm going from 0 to pi over 2, and the function that I am finding the area underneath is cosine x. Alright, so if f of x, little f of x is cosine x, that means that the antiderivative of that is sine x. So the antiderivative of cosine x is sine x. I put my a and my b here because that's what I'm going to plug into that function. So once I've found the antiderivative, I plug in pi over 2, I plug in 0, and what I get is the sine of pi over 2 is 1, and the sine of 0 is 0, so 1 minus 0 is just 1. So the area under the cosine graph from x equals 0 to pi over 2 is exactly 1 square unit. We're going to talk about more examples of this tomorrow, but I just wanted to introduce to you how we are using antiderivatives and the fundamental theorem of calculus. So I will see you tomorrow.